Bismillahirrahmanirrahim. Assalamu alaikum. Today we are going to start lecture number 27th, and in this lecture we will discuss two topics, and these two topics include two-dimensional arrays and the structures. Now before going to start this lecture, we will discuss what we did in our previous lecture. In previous lecture we did the assembly implementation of the stack parameters, how we can use invoke directive to call the procedures, and then procedure directive and also the proto directive. So the procedure directive we used to declare or to define the procedures, and proto directive was used to define the prototypes in assembly language. After that we discussed how we can pass arguments by values and by reference. So in by values we were merely transferring the values of variables or the registers, whatsoever we can call, and by reference we were transferring the addresses of variables and so on. Then we did one example which include the exchange of two integers. For example, if we pass two variables and their addresses whatsoever, so how we can exchange the values of two variables in between them. After that we discuss about the stack frame. This stack frame is an area in the stack which is used to pass parameters. When we pass parameters, or when a procedure receives parameters, or when we pass arguments to the procedures. So these arguments and parameters, what we call them, they are stored in this stack frame. The main purpose of this stack frame is how we can store there and how we can access those parameters from that stack frame area. So there are different methods. We use explicit access to the stack parameters. So we use one register to access these parameters, and then we saw one example regarding passing arguments by reference. So this is the overall review of the previous lecture, what we did in lecture number 26. Now we are going to discuss the outline, what we will learn or what we will discuss during this lecture. So in this lecture we will discuss mainly two topics, as I already mentioned. One is the two-dimensional arrays and second one is the structures. So in two-dimensional arrays we will discuss the basic concept, what is two-dimensional array, what is the representation of two-dimensional array inside the memory. Definitely we are using assembly language, means we are directly accessing the memory, and we know that how these we must know that how these arrays are being stored inside the memory. As we already know that linear arrays, like one-dimensional arrays, they are stored in a sequence of values in a linear fashion in memory. Now we will learn how these two-dimensional arrays are being stored inside in memory. And then there are two ways to access those two-dimensional arrays. One is called the base-index operands, or base index way. Second one is called the Base-Index-Displacement method. So in the base index we will learn that how we can access by using the base register and index register. In 16-bit what will happen, and in 32-bit architectures how we can access the two-dimensional arrays by using base index operands. Then we will do one example about row sum example, and in this example you will see that how we are going to sum all the elements of a row. Then we will discuss about the base index displacement. This is another method. In this method we will see that how we are using base register, index register plus a constant displacement that we will use to access the elements of an array. And then after that we will see the bubble sort algorithm. So this is the sorting algorithm, that is the very basic algorithm to sort all the elements in an array. After that we have the structures. In these structures we will learn how we can define structures, how we can declare structures, and so on. So now we are going to start with the two-dimensional arrays. In this we will discuss about the basic concept, base index operands, and the base index displacement way to access the elements. Now we are going to discuss what is the basic concept of these two-dimensional arrays. Basically a two-dimensional array, or it can be called as a table. For example, here you can see we have rows and columns. For example, this is row number 1, row number 2, row number 3. This is called the scripts, subscripts, which will show, or which shows the index, or the number of a row. Then we have columns. This is column number, for example, 1, column number 2, column number 3, and then column number 4 and 5. So this is basic structure of the logical arrangement of the two-dimensional arrays. However, from the assembly programmer's perspective, two-dimensional array is a like abstraction or high-level abstraction of a one-dimensional array. Now we know that our memory is a linear set, or linear. All the elements in our memory are stored in a linear fashion. For example, here we have addresses and we have data here. So how we store this one? For example, if it is byte data, we store like 10, 20 and so on. So the addresses will be like 0x2100, something like this one, and 0 here, and the next address will be 0x210.1.2 and so on. So all these 5 elements will be stored here. Then the next row will start from 60 and so on, 60, 70 up to some value. So there are 2 methods how we can arrange, how we can represent these two-dimensional arrays inside a memory. For example, if we are going to use the row major, there are 2 methods. One is called the row major order, second one is called the column major order. Now first we will discuss what is row major order and what is column major order. Here you can see we have the first row, then we have second row, and then we have third row. So we have 3 rows and we have 5 columns. For example, and this is like a linear array here, and this is linear memory model. For example, our index, the base address start from here. For example, base address is 0x155 is the address. This will be 151, 152 and so on. So this will continue up to how many byte elements are being stored inside a memory. Now one thing, before going to discuss row major order and column major order, just remember one thing, that these indexes are the subscripts. They can in different languages they start with 1, or maybe they start with zeros, like 0, 1 and 2, 0, 1, 2, 3, 4 and 5, 0, 1, 2, 3 and 4, for example. Even though whatsoever the subscript is, it will show the row and column number, that which element we are going to access. For example, if we want to access the first element and first element of the two-dimensional array, like in the first row and the first column, so this will be, for example, 10. Or if we say second row, second column, then it will be like 70 and so on. So don't be confused. Either we start from 0, either we start from 1, doesn't matter. It depends on the languages. However, here we will discuss what order we are using. But before that, we will see what is row major order and column major order. In row major order, as we can see here, in the first row there are 5 elements. There are 5 columns in the first row. So in the first row we will store all the elements inside the memory. For example, here we have 10, 20, 30, 40 and 50. These are the 5 elements in one row. Then we will store all these 5 elements, which are being shown by this red box or red outline. Here also in this one you can see we have all these. This is the first row. So all the elements here, they are being stored first. Then we have second row, then we have third row. So all the elements of a two-dimensional array or a table are being stored in a linear memory in row order. Like first row we store all the columns of first row, then second row and then third row. This is the most common method to store elements inside the elements of a two-dimensional array inside memory. If you can increase the dimension, like three-dimensional arrays and so on, then this row major order will also consider these rows and so on. However, we are not concerned with the three-dimensional and so on, but we will discuss only the two-dimensional here. So the next method is column major order. In this one, in column major order, you can see here, these columns are outlined with blue box or blue outline. So first column will be stored inside the memory, then second column, then third column, then fourth and fifth column. So here you can see the first column has the element 10, 60 and B0. So 10, 60 and B0 are being stored here. Then 20, 70 and C0, 20, 70 and C0, they are being stored second. Then the third column, then the fourth and then fifth column. Whatsoever the order is, it will occupy the same memory area, same amount of memory. Either you use row major order or column major order. However, the difference is when you access the elements of a two-dimensional array. So here we will discuss the most common method, which is row major order, how we can use this one in assembly language, and what are the methods to access the elements of this array. So first method, or the first way is the base index operand. So by using the base index method, we can access the element of an array. What is base index? This is the one of the way. We have already used this one in the addressing modes. So this is actually the base index addressing mode. So in base index operand or base index mode, we add the two values of two registers, for example, like base register and the index register, to produce the effective address. So whatsoever the base register is and whatsoever the index register is depends either we are using 32-bit architecture or 16-bit architecture, whatsoever the way or method we are programming. And these brackets are important in the base index addressing mode. These are the brackets which we must have to use. You cannot omit if you are using the base index and so on. So in 32-bit mode, any of the 32-bit general purpose registers, they can be used as a base and as an index register. Just like we have EAX register, EBX, ECX and so on. So all these registers, whatsoever the registers you are using, they can be used as a general purpose register. All the general purpose registers you can use for base and index to access the elements. However, in 16-bit mode, the base register must be BX, BP, or these base, because BX is the base pointer and base register and so on. And for the index register, you can use source index or DI or destination index and so on. So SI and DI, you can use any of these two. So either you can use SI or you can use DI. So in 16-bit, you have to use the base and the index registers, which are specifically defined to work as a base and as an index register. However, in 32-bit mode, you can use any of the general purpose or registers whatsoever in the architecture are. Now here you can see one example. So this is one of the example which uses 32-bit mode, and as we know that base register and the index register can be any of the general purpose register. So here, for example, we have defined an array. Inside this array there are three elements: element number 1, element number 2 and element number 3. Here you can see we are not using any of the two-dimensional right now. We are using only one-dimensional here. So inside the two-dimensional, if you want to see here that EBX has the offset or the base address, and ESI has the index value. So offset of an array. So this is the starting address of an array. So next what we are going to do is we are assigning 2 because we want to access the element number, how many offset, how many bytes we have to increase, for example, how many bytes we have to escape from the base, for example. So if this one starts from some address, so the starting address is, for example, S, then these 2 bytes, including S, like S, comma, S plus 1, so this is the starting 2 bytes, they will occupy this value, or this value will occupy these 2 addresses. Then S plus 2 and S plus 3, these 2 bytes will have the value 200 00 hexadecimal value, and so on. So if we want to access the second element, then offset should be twice, means the 2 bytes after the first element. So first element occupies 2 bytes, then this should be the offset. So EA means AX register is the 16-bit register. It will have the value from this location, EBX plus ESI. And we know that how we can calculate the base index effective address by using base and index. So we are going to use EBX plus ESI. From this address we will calculate the effective address, and this effective address will be used to locate where our element is. So this is one way. So we are using this base index to access this element. However, the main thing to note here, we are using EBX and ESI. In the next example, you can see we are using EDI and the ECX. So EDI is one of the register we are using, and it holds the base address, similarly like EBX. So ECX here is the index register, which is the 4. So we are skipping 4 bytes from the base, and after 4 bytes we are going to access the value. For example, if we have first 2 bytes, these first 2 bytes occupy they have hold the value 2000 hexadecimal. Then next 2 bytes, first 2 bytes will have the 100 and so on. Next 2 bytes have the 200 hexadecimal, and third 2 bytes have the value 3000 hexadecimal. If this address starts from 0x150, then the next address will be here, then the third address should be 152, and 53 should be here. So this element, second element, starts from 152, and third element starts from 154, and so on. So these 2 bytes, each of them element occupies 2 bytes, and so on. Similarly, in the third example here, a third method here, you can see we are using EBP to hold the base address, and we are using ESI to hold the offset. So offset is here, for example, 0. So it means we are accessing the element, first element of this array. So here we are not going to displace, or we are not going to shift any number of bytes whatsoever the base address is. We are going to access the same from that address. We are going to access 2 bytes, and so on. Here the base index which we use, it has one major application when we access the structures. These base index operands are very useful for accessing the arrays of structures. Now, what is a structure? We will discuss in more detail in the end of this lecture. However, before that we will discuss what is a structure, and very briefly we will discuss. So a structure is nothing but a group of multiple elements, or a structure groups together the data under a single name. Here is one example, like we have the coordinate structure. This coordinate structure has 2 members, or 2 fields, X field and Y field. And a structure, when we define a structure, it starts with the keyword struct, and ends, and S is the end structure, and so on. And the end line must be similar, like the same name, CORD, COORD are coordinates. So in this structure there are 2 fields, X field, this is upside word, and its offset should be 00, and the next offset is 02 because the word occupies 2 bytes and so on. So the common application of base index addressing has to do with addressing arrays of structures. We will see how we can access the arrays of arrays of the structures and so on. The following is the this one. Here you can see this is one of the example of the structure, and this is the structure definition, and then we are going to declare the variables. We can define the variables of type coordinate type. So this will be our user defined data type. The name of this user defined data type is the COORD, coordinates, and here you can see the number, the name of the variable which we are using to hold this structure is called the set of coordinates, and data type, and this is 10 times. We are going to duplicate 10 times, and these brackets define that there is no value which we are going to assign to the elements of any structure and so on. So there's one loop here. You can see one loop. So this is one of the example where we are going to use the how to access structure elements by using the base index. So the following code loops through the array, and it will display each y coordinate. Definitely we know that our structure has two fields, x, which will occupy 2 bytes, okay, 2 bytes, and then the y is the second field or second member. This will occupy second consecutive 2 bytes. If, for example, if this one has the offsets 0, 0, this one will have offset 0, 2, because 0, 0 and 0, 1 offset, these two are being occupied for the x. Then 0, 2 and 0, 3, they are being occupied by y. So if we want to access the element y, or the field y, or member y of coordinate structure, then our offset, the index should be 2. Index should be 2. So this offset of value y, and EBX holds the base address, or the base of this structure. So here you can define, before that when you can define a structure and so on. So this one, it shows that we have an array of 10 structures and so on. How we can access? For example, EAX will hold the EBX plus ESI. So EBX has the offset value plus ESI has the EBX has the index value, and ESI has the offset value and so on. So we are going to convert this value into the for example, if we want to display that value of y, then we convert from double word to ASCII and so on, and it will be stored in EAX. Okay, the value is inside the EAX, so we are going to convert this one, and it will be stored inside the display decimal and so on. So display decimal is nothing but an empty string or any type of string whatsoever, null terminated. And invoke 0 is the std out, for example, invoke std out. So invoke std out and the address of the display decimal and so on, this variable whatsoever the value is inside display decimal, it will be displayed over the screen. And then the next one which we are going to do is EBX is being incremented. EBX is being incremented size of the coordinate, for example. So for example, we have the how many the next, this is for the first one. Next we start from 0, 4, 2 elements for x, then 0, 5 is the here, so 0, 6 should be here. So the size of this one is size of coordinate is like 4. So EBX is added with 4. So previously EBX was 2, so 2 plus 4 is equal to 6. It means we are accessing this next address. So this address, and this address shows, for example, this one is x and this one is y. So element y of the next array element of the coordinate structure. So similarly, we can access this, and this value of y here, then here is also x and the y. So this is the first element of structure, coordinate, first element, then we have first element, we have second element, and then this one will show third element, and so on. So we can access whatsoever the number of elements are there, we can access all those elements of this coordinate structure. And we are not accessing all the elements, but we are accessing all the elements of coordinate structure to read the value of y. So this is one of the application of the base index operands. Now we will see how we can use the define our two-dimensional arrays. So this is one of the example of two-dimensional array example. So this one shows that we are going to define a variable named table, and here this is an example of linear array or one-dimensional array. However, we will use it as a two-dimensional array. So we can imagine a table with 3 rows and 5 columns. So first row is like this one. This is first row from here to here, and there are 5 elements, means 5 columns are there. Second row is also 5 columns. Third row has also 5 columns, and so on. So here we define, for example, number of columns is equal to 5. We must have some information regarding how many columns are there so that we can easily access the two-dimensional arrays and so on. So the alternative, this is one way to represent the two-dimensional array. The next way is, the alternative format is, you can use multiple lines, because we cannot write all the elements if we have so many elements in single row. If we break it, we can use the data type or type specifier here, or we can use same comma here, and we can continue to the next line up to whatever the number of lines are there. And we know that there should be comma here, which indicates that our line continues to the definition, or whatever the number continues to the next line, and so on. So these two definitions are similar. These are the alternative definitions, so you can use any of these definitions. Now we can know that we can say that we have defined one two-dimensional array. Actually, this is not two-dimensional, this is one-dimensional. The way you access defines that this is two-dimensional array. So here there are like 15 elements starting from 1 0, and the last element is 0 F0. So all these 10 elements are hexadecimal values of 1 byte. They will be stored stored on 15 consecutive memory addresses inside memory, and so on. So the way, if you want to access the two-dimensional array in a row major order, so this is the way how you can access the two-dimensional array by using the row major order. Just recall what was row major order, that the first row will be stored first. This row means all the 5 elements will be stored first, then next 5 elements, and then next 5 elements. So you can define number of columns, or you can define row size. Row size is 5 here because we have it occupies 5 bytes, or it will occupy the 5 bytes, or it has 5 elements, and so on. So the row offset is it's being held inside the base register. So this is the offset value. The offset value, or the starting address of the table B, will be held in the base register, and the column offset will be held inside the index register. So now we are using two. One is we are using the base, and second one we are using the column for the index. So we are using base and index to represent row and column. Then combination of that one, we will access the elements of this two-dimensional array. This following table has 3 rows, the same one, and 5 columns. Now you will see two-dimensional array. So in a row major order, for example, the row size, as we know that we have defined row size, is calculated by the assembler as the number of bytes in each table row. So if we have two-dimensional array, there are 5 elements and there are 1 byte, it should be 5. The row size should be 5. if there are 5 elements or 5 columns inside the first row or any row, and the size of them is like word, or they are defined as a word, 2 byte, then the row size should be 10. So it should define the number of bytes that are being occupied by a single row. So in this example here, you can see we want to access the element at row number 1 and column number 2, row number 1 and column number 2. So this should be, so here you can see that EBX, so the row number 1 and column number 2. So the table's offset should be, or it can be, we assume that we are going to put it inside the EBX. However, you can use any of the 32-bit register. So here EBX has the table's offset and the row offset. So how we can calculate row offset? That EBX plus row size multiplied by the row index. So here is row index. Row size is, for example, 5. So 5 multiplied by 1, and then we have the EBX. So this is the initial address. So we are starting with the initial address plus row size is, for example, 5, and row index is equal to 1. So we are going to multiply them, and this will give us the row offset, that from the base address how many number of bytes we have to skip, and then we have to access that element. And ESI, for example, here will hold the column index, and that column index is equal to 2. Now here you can see row index is equal to 1, column index is equal to 2. So row index and column index, these values are being defined here. Now EBX has the offset, or the initial value, a starting value of the offset. Now we want to calculate what should be the address from where we can access the row element, or row element in the row number 1. Now here, just remember one thing, we are using indexing from 0 row, 1 row, 2 rows, and so on. So you will see here that we are going to access actually we are accessing the second row, but here we can use the 1 as the starting point, 1 is index. So EBX plus the row size, as we know this is 5, and the row index is equal to 1. So 5 multiplied by 1 plus the EBX, whatsoever the addresses. So this will give us the row offset. And then ESI is the column. So if we use the column index, it is equal to 2. So ESI plus EBX. So this will have the 8080 hexadecimal. If we just go to the next slide here, you can see. So here is the row from here to here. This is the first row. However, its index, the row index is equal 0, and the second row will be from here, 1, 2, 3, 4, and 5 elements. So this is the second row, its index is equal to 1. Then we have third row, its index is equal to 2, row index, and so on. So here what we are going to do, if for example our base address is equal to 150 hexadecimal, and what we do here, the base plus we have the row index multiplied by the row size, and so on. So we have row size equal to 5, base is equal to 150, 5 multiplied by 1, so it should be 5. So the 155 is the row offset, or the offset, which will start from here, from this. So EBX will have this value, means EBX will point to this address, which is 60, and element number 2. So element number 2 means element number 0, element number 1, and element number 2. Element number 3, element number 4. As I mentioned at the starting of this lecture, that the indexes are the row index and column index, they start from either 0 from 1. Here we are using the 0 starting address as a row index. Some languages, they manipulate this one and then they use row index equal to, means starting row index is 1, not 0. So here we are using 0. So 2 is the offset. For example, if we use effective address, if we calculate, it should be 155 plus 2, so it should be 157. So EBX plus ESI, they will point out to this 80. So this value will be stored inside the AL here. So row index, starting row has the 0 index, second row has 1 index, third row has 2 index, and so on. Starting column index start from 0 column, 1 column, 2 column, 3 column, 4 column, and so on. So this is the method which we are using. So here in this example, you can see we have defined, we have used this base index method to access the element of a two-dimensional array. However, just please remember that there are no two-dimensional arrays. This is the abstraction. Abstraction means we are going to access them at the higher level. We assume that these are considered as two-dimensional. At the basic level, this is one-dimensional, definitely. This is only the abstraction, how we access them, how we access the elements of elements inside them from the memory. So it's very clear from this example. However, we will move to the example like calculating the row sum, and this should be very much easy. So for example, if we want to calculate the sum of all these rows, any of the row, for example, this is the row 1, row 2, and row 3. Row 1, row 2, 3, and row 1, row 2, and row 3, but their indexes should be 0, 1, and 2. We have 5 columns starting from the index. Column has index 0, 1, 2, 3, and 4, and so on. So this is how we divide abstract, means abstraction level. We assume that these are the columns and these are the rows, and row size is equal to 5, and definitely this must show the number of bytes occupied by a single row. Here is display 1. This is disp1 is a variable. This variable is 20 bytes, and this will show the result or the sum of all the rows. So this is the message that will be printed out. Here what we are going to do, that EDI is the row number, and the EBX, or this is the offset of the table. So this is the starting address. ECX is the row size, and we are going to call sum, calculate row sum. Now we are going to call one array, one procedure, which has the subroutines or the statements to calculate all the elements inside a row. So row number is 1, its address. So EDX has the row number, EBX has the starting address, and ECX has the row size. We know that we can use this whole all these 3 registers, and definitely EAX will have the sum. So we'll see what is inside the calculate row sum example here. So here is the row sum procedure. Inside this procedure, we see that EBX, ECX, EDX, and ESI. So it will receive this whole procedure receives the EBX in the table offset. Table offset inside the EBX. Row index is inside the EAX. This is the row index, and which was equal to 1. This row index was equal to 1, and row offset, the starting address is inside the EBX, and ECX has the row size, and this row size inside the in terms of bytes. So this is the row size. Now what we are going to do, first we calculate the index of the row, from where we are going to start our rows, the address, for example. So we are going to multiply ECX, the row index. This was row index is inside the EAX. As we know, EAX has the row index, and we are multiplying the row size inside the ECX, so the result will be again inside the EAX. So we have multiplied row size and the row index. Now what we will do, we will add this one, EAX, because this one has the row index multiplied the row size. We will add with the EAX with the EBX, the base address. So now we have the starting address of the row which we are going to add. This is the starting address, and we are going to EAX accumulator is moved with 0, so we are going to reset the value of EAX register with 0, so that it should be 0. We will store the new sum value. ESI will have the common column index. So here what we are going to do is we are going to move 0 extended EDX byte pointer here. So we are going to convert this one whole. We are to get byte from EBX plus ESI. So EBX has the row offset, the starting address of that row, which we want to calculate the sum, and plus the ESI. ESI right now here is 0. So 0 plus these the EBX, whatever the starting address is. So it will access that row and the first element, or the element column index with 0. So this will be from that address, 1 byte will be moved to the EDX. Now what we are going to do, we are going to add EDX with the EAX. So first initially EAX is equal to 0, EDX will be added, the first element or the value, first value will be added with the EAX. Now we are going to increment ESI. You can see previously ESI is equal to 0, and now ESI has the value incremented, like it will be 1. So we are going to multiply EBX or add EBX plus the ESI. So here you can see ESI will be equal to 1. So EBX plus ESI, starting address of that row, and plus 1. So this will be the next byte that we are going to read. So in this manner you can read all the number of bytes. So here should be some condition that you can use to terminate that how many number of bytes you want to sum. So you can have condition that that will loop to the L1 to terminate this whole loop. Now ESI will continue until whatsoever the number of bytes you want to access for the number of bytes are there. So this is one way you can calculate the sum of all the rows. However, in case if you want to access the 2 byte or the word type, then there should not be only increment in ESI, there should be addition of 2 in the ESI and so on. So it should not be a next byte in a row, it should be next 2 bytes in a row. Initially ESI should be 0. In the next iteration you have to add 2 in the ESI. In the third iteration next again you have to add 2 in the ESI and so on. So ESI should be 2 bytes, depends on the type of the element. If it is double word, then accordingly you have to add the value inside the ESI. Now second method is called the base index plus displacement. Now there are 3 things. As we know that these 2 are base and index, we already know these 2 can be any registers, general purpose registers in 32-bit architecture. Now this displacement is the third value which we are going to add here. So this displacement you can see here, base, index, this can be any register, this can be any register. However, this can be any variable, name of a variable, or it can be a constant. How we can use this one? Here you can see that these in 32-bit registers, there are 32-bit general purpose register. They can be used here for base, for index, and so on. And the common formats is like displacement. Displacement can be a register or can be a variable, name of the variable, plus base, and plus index. So these are the three things that we have to aid with the aid to calculate the effective address. So the effective address is now being calculated from three things. One is called the base value, index value, and the third one is called the displacement. In this example, now you can see here. So here we have example. We want to access the same example as you saw in the previous one. We have row index 1 and column index 2. So we want to access the element of row index. So this is the from here to here. This is row index 0, and this is the so we have 1, 2, 3, 4, 5 elements. So from here to here we have row index 1. So column index start from 0, 1, 2, 3, 4, and here we have the column index of 0, 1, 2, 3, and 4, and so on. So similarly we have row index number 2 and so on. So we want to access this element 80. We want to access this element by using the by using the base index and displacement. So row number is here, column number is here. So what we are going to see, number of columns multiplied by row number. So number of columns is a variable which shows that how many columns are there. For example, if we have 5 columns, so it should be 5, and row number is equal to 1. So if we say 5 multiplied by 1, so this will be 5 inside the EBX, and the column number is equal to 2, so is inside the ESI. Table has the base address or the starting address. So EBX is equal to 5, ESI is equal to 2, so it's equal to 7. So table shows is a variable. This variable shows the starting address is equal to 150. So 150 plus 5 plus 2, so it is called 157, 157. So whatsoever the value which is stored at 157 will be accessed, and the value will be transferred to the AL. So here you can see in this example we are using the table. This works as a displacement, and then EBX is the base and ESI is called the index. So base here has the value row number multiplied by number of columns. So how many number of columns are there inside the row? So it will be multiplied with the row number, and the column number is 2. So we add all these, and then we can get the effective address. So here you can see the table EBX, for example, it shows this starting element here of the second row, and the second element of this the element number 2 of the second row has the value at the 157 address. Now we have the one example here. In this example you will see the algorithm is called bubble sort algorithm. Now bubble sort algorithm is very easy. What we do, that for example we start with the, I can show you here in the example. So this algorithm basically sorts all the elements. This bubble sort, inside this bubble sort algorithm, each pair of elements, they are being compared. So each pair of adjacent values are compared to each other and exchange if the values are not ordered correctly. If the first value, for example, is greater than the next value, if the first value is greater than the next value, then we exchange. Here you can see 3 is greater, the first we are starting from here. So compare these two. Is 3 less than greater than 1? Then we exchange. So we have exchanged 3 here, 1 is there. Then we compare second element with the third element. If this 3 is greater than 7, no, leave it as it is. Then we compare 7 with 5, meaning the third element with the fifth element. So you can see here, so 7 is greater than 5, so we are going to displace or the swap the elements. Similarly, we can continue. So here you can see we are starting from the first element. So compare here, one iteration, 1, 2, 3, 4, 5, 6, and 7 iteration. Inside these 7 iteration, and the number of elements are how many? 1, 2, 3, 4, 5, 6, 7, and 8 elements. Total number of elements are 8. The number of iterations, the number of iterations here are 7. Total number of elements are 8, and the number of iterations are 7. Now, 1 less than the number of elements. This is the whole complete one go in the one complete comparison. Now, in the next phase, this is the first phase. In the next phase, we will continue. But what happened in the first phase? You can see here, wheresoever you will have the highest value in this array. So here you can see 9 is the highest value inside the array. This highest value will be moved to the last element, to the last value. So here you can see, wheresoever we have the large elements or the large value, it will be moved to the end in the first iteration or first pass. In the first pass, it will move to the last position. In the second pass, the second largest element or the value of the element who is the second largest value, that will move to the second last position, and so on. So this iteration will continue in the first, and we know that in the first pass, this largest value has moved to the last position. Then we don't need to compare in the second pass. We can compare up to here. So what should be the number of comparison? 1, 2, 3, 4, 5, and 6 comparison. So second pass there will be 6 comparison. Third pass we have 5 comparison, and so on. So this is actually the bubble sort algorithm. If you will take the course of data structures, this will be the one of the example, one of the sorting algorithm. This you will use to sort the elements of an array and so on. So in this bubble sort algorithm, this is the pseudocode. N is the array size, total number of elements in an array. Cx1 is the outer loop, Cx2 is the inner loop. So this will show the pass, one pass or one go. How many number of passes do we need? How many times we have to repeat this comparison? So the number of passes, this is the how many passes. This is one pass, and this will have the total number of passes that we have to go. So Cx1 is equal n minus 1. Initially we are starting. How many comparison do we need? So we are starting Cx nx1 is greater than 0. If it is greater than 0, then what we have to do? ESI is equal to address of an array. So Cx2 is equal to Cx1. So we have to continue these number of passes, until we become Cx becomes 0. So this one is if the first element is less than the next element, or we can say the first element is greater than the next element, then we can exchange, and we add ESI, so and decrement Cx2, and we continue this loop. So this is one of the example. This is the pseudocode, and you will see the same example inside an assembly language. So here you will see the bubble sort implementation inside an assembly language. It is going to use 3 registers. One is the EAX, ECX, second one is the ECX and ESI. So ECX has the count value. Whatsoever the count value is, we are going to use this one. And array has the value. Array has the starting, so points to the first element. So array has the offset value, or it shows the offset value or the starting address. So what we are going to see, this P array are pointed to the double word. First we decrement ECX, how many number of counts we want to continue, or how many number of passes do we need. to continue this one, and we will continue until we have the the whole array is being sorted. So for example, here we have the ECX. We are going to decrement because we cannot continue till the whole number of the elements. It should be 1 less than the, if there are 8 elements, the number of comparisons should be 7 in the first pass. In the next, the number of comparison should be 6, and so on. So right now, for example, we have this 7 value for example this one. So we push ECX. We have stored this ECX inside an stack. So for example, 7 has been pushed, and we are using this ECX. Now how we will use ESI is has the starting address of an array. So ESI is the starting address. So what we will do here, move EAX, the ESI. So EAX is the value of ESI. So get the array value. So we are getting the first element. Compare ESI plus 4 and EX. So if we compare that, compare a pair of values like the second element and the first element. So greater than or equal L3, it will move to L3 if second element is greater than EAX. Okay, so if it is ESI is less than EDI, then skip. Otherwise, we have to exchange EAX and this element, the next element, and move EAX to this ESI and so on. Exchange the pair. So what we do, we move or exchange the value of whatsoever the value of ESI, we can move here, or we can move the value of EX to the next ESI and so on. So here it can be any logic you can use. Next, in case if we have this one, the 8 ESI plus 4, so whatsoever, even if you increase, how can you say, the even if you just like either you exchange or do not exchange the values, but we have to access the next element, or we have to start with the next element. So ESI should be incremented with 4 because here we are using the double word. So double word is, so we are going to move to the next element. So we have compared the first 2 elements, 0 and this one. Now we are going to compare this element with the next one. So the value or difference is 4 bytes. So ESI, initially ESI was equal to the starting address, and plus 4 it was compared ESI plus 4. Now we are going to increment ESI. So next element is being compared with the third element. So this is the first element, second element. So second element is compared with the third element. So it will loop. Now before going to we are going to loop here to L2. This will continue up to 7 number of times. When we use the loops, then definitely the CX, ECX will be reduced, and it will continue until ECX is equal to 0. So, so it will repeat 7 times. It will sort this array for 1 pass. Now, how the next pass will start? So when this loop is over, when first pass is over, we are going to pop this ECX value, it was 7, and we are going to move again back to the L1. So now the value of ECX is, we popped is 7. It has been moved because previous value of ECX, whatsoever was there, it was decremented again and again, and it became 0. So we have popped this value. Now we have got the updated value, or the previous value of which was 7. Now when we pop this ECX, definitely it has been decremented, so it will have the value 6. So this whole comparison will continue 6 times. Then again next time we are going to push, then this will be here, 6 will be here. So 6 comparison will go on during this internal procedure, internal loop, and then 6 has been stored, so we will pop 6. And then when we loop to L1, then definitely this 6 will be decremented, it will become 5. So number of comparisons will decrement up to 1 comparison, and so on. So this is very basic example about the bubble sort, and you can use this example to sort the elements of an array. This was one of the examples. You can use the accessing methods. Now we will have the introduction about the structures. You can use these structures to define user-defined data types. You can hold multiple elements which are of multiple data types under a single name. So we will see what are these structures, how we can define structures, how we can define how we can declare structure variables, and how can we refer the members or the fields of those structures, or how can we refer the structure variables. What is structure? A structure is nothing but a template or a pattern given to a logically related group of variables. So for example, we define logical structure here. There's employee ID. So the name of this structure is employee, for example, employee, and then there should be ID of the employee, salary of the employee, and the after that उसके बाद जो होना चाहिए salary के बाद for example age होनी चाहिए, and there are so many other particulars. So there are multiple fields which show the employee. For example, age. Age is one of the field which we can use. So field is nothing but a structure member containing a data. So there are different names. You can call them fields, you can call members, you can call the variable of this structure, and so on. But field and the member, they are most commonly used are words which are being used for this one. So program access to this structure. So entire structure can be used to be passed as a complete unit, and individual fields can be accessed by the program, by a program. So we can either access the whole structure, either we can access the individual member or the field of the structure. This is very useful way to pass the multiple related arguments. So these are the multiple arguments which we want to pass to a procedure. For example, if we have the employee directory, so if we want to pass this one whole employee, all the members related employee into the, so we do not need to pass each of them, we need to pass only the employee, whatsoever the variable of type employee is there. So how we can use this structure? Using this structure involves three sequential steps. First step is define a structure. Second step is declare a structure. Third step, write a runtime instruction to access the structure. So you can manipulate the values, you can access the elements of those structure, either you can add values, you can access those values, you can assign new values, and so on. So first we will define the structure, then we will have the structure variables, we can declare the variables of type that is structure, then we will have the subroutines that will access the members of those structures. So this is the syntax of that structure. So first, as we already saw the brief introduction during this lecture, the name should be similar at the starting of the structure and at the end of the structure. So name and struct and s or and structures define the whole region where the members or fields of these structures are being defined. So this name will be used to declare variables of this structure type. So field declarations are identical to the variable declarations, and so on. So here you can declare any variables like of type byte, word, double word, so on. Here we have the, for example, the same structure which you saw in our in the starting few slides of this lecture. So we have coordinate structure, and the name of this structure is coordinate. It used by actually in the next coming lectures you will see this coordinate structure will be used when we use the MS Windows programming library. So it has two members or two fields, x and y. They define the screen coordinates. So definitely our whole screen has is divided into x and y coordinates. So there are pixels. These pixels are defined in the x and y coordinates. Even you can define the position by using this coordinate structure. So here in this example, coordinate is the name of the structure. Struct keyword or directive declares or defines that this is the structure. There are two variables or two fields or two members, X and Y. These are of type word, means 2 bytes. Offset is 0 for this one, offset is 2 for this one. And then the next structure example is the employee. So the employee structure, the name of this structure is employee, and there is the ID number is of type byte. This one is the array of all these bytes. We define 1, 0, 0, and this is the default value, for example, you can call it. Last name is second element or second member or second field of this structure. This is called the last name. It's of type byte, duplicate 30 times, and then year, so it's a word, and initial value is 0. Salary history, there are multiple salaries, last 4 salaries is double word, and there are 4 elements. So you can see here, first element is of type byte, second element is of type byte, third element is type word, fourth element is called double word, or fourth field is double word. So this is the structure inside, how this structure will be stored inside memory. So first 2, 4, 8, 16 and 2, 4, 6, 8 and 9. So first 9 bytes will be occupied by the ID number. Second 30 bytes will be occupied by the last name. Then first word here, 2 bytes will be occupied by the years, and then the salary history, double word multiplied by 4 times will be occupied by this salary history. Then we are declaring structure variables. For example, structure name is used as a user defined data type. For example, if we declare a variable, in the previous one you saw that ABC double word, so we use double word, we declare something here. Here you can see ABC is the name of the variable, this is the data type. Now here we will use any of the variable, CORD11, and the structure name will be CORD, and we can assign any values here if we can assign. Otherwise we can use insert or replacement initializers between the brackets. What we are going to initialize, the value should be inside the brackets. Otherwise we can use empty brackets, not the question marks, because we have multiple members, so we can use either question mark, either we can use closing and starting, opening and closing angle brackets. So this will initialize the empty structure without any values. So in this example here you can see we have inside data section we have point 1, it's of type coordinate, and we initialize 5 for X, 10 for Y. So this is the initialization value we are initializing. In the next point 2 variable is of type coordinate. This is the second variable of the structure coordinate, and we do not initialize any value inside this point 2. Third variable is of type worker, and it's of type employee, and we do not define any value for the this worker variable. So here you can see we can define the initialize and error fields. For example, previously you saw that how we can initialize by using empty angle brackets. You can define any variables, any values inside these angle brackets. However, if you want to define the employee array, so here you duplicate, you can use duplicate operator to initialize one or more elements of an array field. Here we're using employee, EMP of type employee. So we are not using here anything, nothing for the third 3 members. For the fourth member we are using 2 times duplicate to 20,000 and so on. So this will initialize the array of the last salary history array. You can initialize by using duplicate and so on. In case of employee as we know there are 4 elements inside that one, so we can duplicate twice. Here the array of structures. So previously you saw that how we can initialize the elements who are used as an means arrays who are used as a field or elements. Here we can see that how you can declare or define the arrays of structures. So arrays of structures is nothing but similar. An array of structure objects can be defined using the duplicate operator. Initializer can be used here. So number of points is equal 3. So all points is a variable of type coordinates. 3 times we duplicate. So there are 3 members of this all points. So for example, all points, first element has the 2 things x, y, all points 0, all points 1, all points 2. So there should be x and y. For the third, there should be x and y, and so on. So these are the 3 members or 3 elements of all points array, and this all points is of array. So this all points is an array of type coordinates, and there are 3 elements of this array. First, all the elements are assigned with the value 0, 0 for x and 0, 0 for x and 0 for y. So all the elements. Second one is the RD department is of type employee, and there are 20 employees whose values are not initialized here. And accounting is another value, another variable of type employee, and there are 10 employees, and these 10 employees were assigning their salaries. 4 elements of the salary array, salary history array, and their value is like 20,000 and so on. So referencing how we can refer the variables or the fields of that structure. So for example, here the same employee structure is being used. There are last name has 30 bytes, year is a word type. We can see number of bytes, 9 bytes, 30 bytes, 2 bytes, 16 bytes, and 57 bytes is total. This is 16 bytes because there are 4 double word. So 4 double word multiplied by 4, so it is because the size of double word is 4 byte. And this array has the 4 elements here. So 16 word is 2 byte and so on. So if I want to access the elements, how can I access? For example, I've already defined a variable named worker. So this worker has 4 elements: ID num, last name, year, years, and salary history. If I want to say that EX type, what is the type of employee? So it will give me the number of bytes. So type of employee, we know that it's 57. If I say size of employee is same as the 57. Size of worker, this one is same 57. So this is the complete whole. Either you are going to access the whole structure or the element of this structure or the variable of a structure. However, if I want to use the salary or salary history here, then what is the type of employee salary history? So its type is equal to 4 because type is equal to double word. If I want to say length of, so number of elements are 4. So this shows the number of elements. If I want to say size of, so what is the total number of total size? It will give me 16 because this is the total size. So you can use either length of, you can use type and size of. Their values are here. So this will give you what is the type of salary history in bytes. It will give you 4 because this is the double word type. Then length of, total number of elements is equal to 4, and size of is 4 multiplied by 4, total number of elements and size of each element. Here we can use either move instruction whatsoever, the workers.years into dx. Either we can use worker.salary comma 2000. So first salary, you can assign this 2000 to the the first element, you can have the second element, salary plus 4, worker.salary history plus 4, and then edx has the offset worker last name and so on. So this is the way you can assign, or you can read values from the assign values to the elements or the fields of an structure, or you can read values from those fields of the structure. If I say offset worker, so this will give you the starting address, so I can use imply pointer to the esi.es, so I can use this way to access the element which start with the years element, the name is years and so on, and the value will be passed to the ex. Just try to avoid this this type of type esi, because we don't know exactly from where to start, because imply and this is pointer to esi, so pointer is more important, you have to use. So now we will summarize what we did in this lecture. In this lecture we gone through, we discussed. So now we will summarize what we did or what we discussed in this lecture. First, we discussed about two-dimensional arrays. So the basic concept of two-dimensional arrays, row measure order and column measure order, how we can represent the two-dimensional arrays in row and column measure order, then base index operands to access the elements of row measure or the two-dimensional array, and then base index displacement method to access the elements of an array and so on. Then we saw the bubble sort algorithm, one of the algorithm which is being used to sort the elements. Then we have gone through the structures, a very brief introduction about the structures, how we can define a structure, how we can declare variables of the structures, and how we can access the members of a structure. These are the references you can refer for this lecture, the chapter number 9 and chapter number 10 of this reference, the assembly language for Intel-based computers. So the book is Kip or Irwin. So most of the slides are also taken from this book. So till next lecture, Allah Hafiz.